Hello, everybody, and welcome to our last and final class. Whoa, I can't believe this is already the last and final class. And yeah, before we begin, last time I said I'm going to put my teacher head when I begin. And I didn't have a teacher hat, and you asked for one. So this time I'm actually going to put on my teacher hat, and then we can begin. So yeah, hi, hello everybody, and welcome to the final class of the Raspberry Pi Pico deep dive. And today I'm going to start by sharing my screen as usual, and then fighting with Zoom to make sure that I can see the chat while the screen share is on. I think I just closed the chat. So just one more moment to figure out Zoom. Yeah, okay, I found that. And thanks for the feedback on the teacher hat. So yeah, so before we dive into the agenda, which is pretty intense as usual, even more than the usual, I guess. I love your jokes on the chat. I want to just say that I'm really impressed with two of the course students, I think, PK and Scribble. They have been sharing their experiments with getting optimizing MicroPython code and creating a MicroPython module that would allow you to, instead of like typing memory addresses and memorizing the memory addresses of the peripherals, it's called LSHW, and it has like all the constants with all the memory addresses of the peripheral registers. So they did super cool work profiling it and making it load super fast. Yeah. You can find the details in the Discord, or if anyone wants, they can probably put the details here in the chat. And we'll start by talking a bit about the final project. That was actually a tough one because I wanted something that was never done before. And that's why I had to make sure it's even possible to do it. And I'm pretty certain it is. It's going to be a little bit challenging, and it's going to be based mostly on today's lesson. So today we are going to talk about PIO, that's the Programmable IO, a unique feature of the Pi Pico that everybody was excited and still is excited about. And what you are going to try to do is to use the PIO to create retro TV set, or to control a retro PAL TV. And the project, I don't have all the details like in the document yet, but they will be here and also like linked from the Hackaday course page probably by the end of the week. But the idea would be to create something like Pong that runs on a legacy PAL composite video TV. And you can, of course, test it against a real one if you have. I don't. So you will also be able to test it in the simulator. We have a simulated TV. And actually, just yesterday, one of the community members sent me something really cool he did with a TV. That's a Pong game, a retro Pong game. So that's what we are also going to do. You are going to create a Pong game using this TV. So there is this TV element, and I will share the walkaway project template so you don't have to worry about the connections, probably with 2 buttons, or I don't know. We'll see about the inputs, but let me just show you what he did. I think it's extraordinary, and honestly, I don't expect everyone to get to that level, but as long as you can get some basic variation of Pong on the screen, that would be great. And of course, you will have to use the PIO. So yeah, that's the Pong from Anderson. I really love it. It's with sound and everything. You can probably hear it. Yeah, I'm gonna fail just so you see how it works when someone fails. Boop. Okay, so yeah, I will just post this if you need some inspiration. This is, of course, not using the Raspberry Pi Pico. It's using the Arduino simulation, but you will do it with the Raspberry Pi Pico. So let's just share this link, resources. Yeah, and we'll fix out, yeah, it's TV Pong. Okay, cool. Yeah, if you want to support NTSC, you can definitely do it. And if you want to run it against a real TV set, if you have a real physical TV set and you want to try it, then I will include instructions how to make the connections. It's super simple, like 2 wires and 3 resistors. You don't need the resistors here, but for the real TV set, you do. And we'll talk about more about the final project at the beginning of the Q&A session, like how to approach this. I just wanted to give you a quick heads up of what you will be doing. And I think with that, let's move on to talking about PIO, the reason we are here today. So PIO is a very unique and powerful feature of the RP2040. For me, it's the first time I see something like that on a microcontroller. And I spent the last week writing the simulation for it and playing with it. And I will share the link to the recording of how I implemented the simulator if any of you is interested, so you can watch it later. But for now, let's just go into the datasheet and do what we like to do, just dive in. So PIO overview, there are 2 identical PIO blocks and then blah, blah, blah. And you can see each PIO blocks as actually have 4 state machines, so 4 like small processors that can run code. Basically, you can implement a bunch of protocols with this PIO. And before we dive in, I just want to give you a very high-level overview of this environment of the PIO. So there is like a bunch of instructions. You can see we have like, there are only 9 instructions. So it's programmed in its own sort of assembly language, and you probably recognized move and jump from the ARM assembly, but here they have a slightly different meaning. So we will get to that in a moment. And other than that, there are also registers. So just like the ARM, we have registers and we have instructions. And before we dive into the instructions, let's take a quick look at the registers. So that's, where is that? In the programmer model, registers. So basically there are like, it says a small number of internal registers, and it's pretty small. There is the output shift register, OSR. There is the input shift register, ISR. There are 2 counters, but don't worry about them for now. And there are also 2 scratch registers, X and Y. So in total, 4 32-bit registers, ISR, OSR, X, and Y. That's like all the registers that we have. So we have 4 registers, and there are also like those 2 counters, but as I said, they are not general purpose, so let's not worry about them for now. And there is also like 9 instructions, so it's really minimal assembly language. But despite being minimal, it's pretty powerful. I figured out you can write pretty complex programs with just a few instructions. And that's because each instruction has like a lot of options, and there are like a lot of configuration options for the state machine. So you can achieve a lot of things by like combining different configuration options with different instruction options. There are like a lot of combinations. Then we have those like small machines, like those PIO processors that are running, and they are running in parallel with the main processor. And I think my first question when I first saw the PIO, after I like look at these instructions and the registers, is how do they communicate? How is my code running on the Raspberry Pi Pico and the microcontroller going to speak to the PIO state machines? So the first thing, there are like 2 main ways of communications. The first way is sending 32 bits data between the or up to 32 bits of data at a time between the program, your code running on the Pico to the PIO state machine, and then the other way around, sending from the PIO state machine to your program. And there are like two, I think we can see them here. Yeah, there are like two, by the way, this is like all the registers again. There are like two FIFOs. So there is like this TX FIFO. So your code, your Pico code can write data to that's the system, to the TX FIFO, and your machine can read from it. And then there is also the other way around, which is the RX FIFO. So your PIO code can put data into this RX FIFO, and then the system can read from it. So there are like two 4-entry FIFOs that are used to communicate between each state machine, each PIO state machine, and the system and your code. And we'll use them extensively. We'll see them in a moment. And other than that, there is also a thing called IRQ. Basically, these are like bits that the machines can set to notify your program that something has happened, and they can also like notify other machines. So they can set an IRQ flag, and that would raise an interrupt in your code if you listen for that IRQ. Or another state machine can also listen, and that's a way to synchronize two state machines. So that's how the machines communicate with the other peripherals on the device, through those two FIFOs and through the IRQ flags. The machines have no access to the main memory or anything like that. They can't read and write from the memory, and they have a very small read-only instruction memory. It's read-only for the machines. The machines can't update their own code while they are running. And if we check out this, we had it here, I think. Yeah, they are like all those 4 registers we were talking about: out, in, shift, and OSR and ISR, X and Y. And there is also like a PC program counter. And you can have up to 32 instructions in each PIO. So that's not a lot, but it's still able to maintain, you can still write a very useful program with it. And we'll go real quick over the instructions, and then after that, we'll start writing code so you can see how they are used in practice, because just reading about the instruction doesn't really give you the mental state you need to have in order to write PIO code. So they are like, let's start with the beginning, just one by one. Jump instruction that jumps to a different address, and there are only 32 instructions, so that's why the address field is only 32 bits. And you can have conditional jumps, like you can have if x is 0, or if x, is not 0, is 0, yeah, or if y is 0, or you can jump if x is not 0 and it also decrements x. So you can jump based on a condition or always to a specific instruction out of the 32 that you have available, like the 32 slots. Then there is a wait instruction, which just halts the program until some condition is met. So it can wait for a GPIO, for an IO pin to change state, or it can wait for an IRQ that was, so another state machine can set an IRQ, and then it would wait for that IRQ to be set or to be cleared. Then there are like 2 interesting instructions, in and out, and their name is a bit misleading. In is basically, they are both a way to shift data. So you shift an arbitrary amount of bit, let's say 8 bits, out of this input shift register, or in case of in, you actually shift them into input shift register, and you can shift them in from several sources. And out does the opposite. So it shifts a bit out of the output shift register, and you tell it how many bits to shift, and you can write them to various sources, like to the GPIO pins, or to X, or to Y. So this way you can just take a few bits at a time and process them instead of like working on 32 bits at a time. So that's very useful if you need to shift stuff, and you usually do. There is like push and pull. So push takes the content of the ISR, and I always get confused between the ISR and the OSR. I always go back to the datasheet to remember which instruction works with which register. But generally, ISR is like input from the world into the PIO that goes eventually into your program usually. And OSR is the other way around, output from your program into the PIO that eventually goes to the GPIO pins usually. So push pushes the content of the ISR into the RxCFO, so it gets the data that you have in ISR and sends it to your Pico program. And pull does the opposite. It takes one piece of data up to 32 bits from the TXFIFO from your PIO Pico program and loads it into the OSR. So that's your way, your main way to transfer data between PIO and your program. Then there is move that just copy data between registers. It can also do fancy stuff like execute instructions and set the PC, which is like jump. And it can also do like some calculations, like it can bitwise note the value that it moves, or it can reverse the bits. And finally, there are two more instructions. IRQ, just setting an IRQ flag, so a way for a machine to let another machine know that something happened, or to let your program know that something happened. And set is super simple. It just gets a value, 5 bits, so 0 to 31, and it can put its value in one of those registers, or send it to the output pins or pin directions. So that's the instruction set in a nutshell. One more thing before we dive into coding. Those machines have their own clock that is derived from the system clock. And there is like a register where you can define how fast this runs. So I think it's in functional details, clock dividers. So we can read all the details, but basically you have like a number and you can divide the system clock by that number. So the system clock by default is 125 megahertz. And if you divide it by 125, for instance, you will get 1 megahertz clock for the machine. And you have 4 machines in each PIO block, and each can run in a different clock. So that's pretty cool. I think the slowest frequency you can run is dividing by 65,536. So that's around 200 hertz. That's like the slowest a machine can run. So each machine can run in a different clock, and you can set a clock to almost any arbitrary frequency between 200 and the system clock. I think this you have like also fractions in the divider, so most frequencies are available. And you usually don't have to worry about it yourself, because there are like APIs to do that. Cool. So we have like spoken for like 15 minutes about the basics of how PIO works. Let's write some code. So in order to write some code, we have a PIO assembler, and that's like, it's described here, but basically it's a small language that helps you to write PIO code, and that PIO code compiles either to C, so you can use it in the C SDK, or to Python, or to Ada. I don't know who is using Ada nowadays, but it's a thing apparently. And yeah, and then you can also like, there is a tool that's called Pioasm. It comes as part of the SDK, but last week I created an online version of it. I will post the link here so you can use it. And it basically runs it in the browser, so you don't have to worry about like compiling the SDK and stuff, and also get in live feedback. On the left, you have an input, that's your PIO program. And on the right, you can see the generated C code, Python, Ada, if anyone is still using that for some reason, and Hex. just the hex codes of each of these 3 instructions. And this section is specifically for the CSDK. We are not going to use the CSDK for today. We'll just use Python because it's easier and you get faster feedback. That's my favorite way to prototype PIO code. But we are still going to use this tool. Let's just reload it to make sure we have the latest and greatest version. I fixed a couple of bugs they had with the Python code generation. And our first program, yeah, we can probably leave this out because this is like code that only gets into the CSDK. So we can just, yeah, remove it and it shouldn't affect the other generated code. And our first program, let's call it Echo. And what this program is going to do is just get information from your code and return it back. So we can pool. So pool would read data from the RX FIFO. Actually, this is just a demo program that comes with Pioasm. So we sort of used it as a basis. So we are going to pull and then we want to push. But so every time somebody sends us data through the FIFO, we'll get it in pull and then we can push this data. But the thing is, if you take a look at the registers, you will probably note that pull hold on, yeah. So push pushes the content of the ISR and pull loads into the OSR. So that's different registers. So we load into, let's write it here as a comment, into OSR, and this is from ISR. So obviously we're not going to get the same data. And for that, we are going also to move ISR, OSR, just to copy the data. And let's see if this works. So don't actually even need this loop. There is the thing where if the program gets to the end, it wraps around. That's represented by the wrap and wrap target in Python. But you know, we have this label, so why not? And what I'm going to do now, we can just take this and, you know, copy it into MicroPython, and that would run, I guess. Or yeah, it loads, it runs, yes. But at this point, we just created the assembly code. So if I type echo, we'll see it did something, but yeah, it created some object with the instructions, but it still didn't create a state machine. And creating the state machine is up to us. And let's start by doing it here. So in general, we want to create a state machine object. And there is like this documentation for the Python SDK with some examples. That's how PIO support. I will post the link in case you don't have this. Yeah, they have a bunch of examples, so I usually just copy from here. This is how you create a state machine, just creating a new state machine object. So let's create it, and that's the name of the index of the machine, 0 to 3, you have 4, the name, then the frequency, how fast the clock runs. I said it can be from very low to very high, but if you set it to very high in the simulation, it will slow down the simulation. And this is not important for this current demo. And then I also need to activate it. So sm.enable should, or I think it's .active, not, oops, yeah, .active, yeah. .active should enable the state machine. So yeah, let's do that and run it. And then I can type in the REPL sm.put and put a value, let's say 15, and then I can sm.get, and hopefully it stacks. Yeah, I didn't get the same value. So I must have done something wrong, I guess. Let me see what could be wrong. If you have any idea, let me know. Otherwise, we'll just probably move to the next, or actually, I forgot to mention, yeah, let's try to put another value and, oh yeah, sure. No. The problem is that this is like spatial syntax. You don't have to define all these variables. They are like handled by this ASM PIO decorator. You can check out the source code for MicroPython, the rp2.py. If you want, I will show in the Q&A cool stuff. But I just forgot to set up the state machine by setting active to 1. So I think that would work now. Let's try to put there 15 and sm.get, and we get 15. And then I can boot another number like 25 and get, but that's not interesting. To make it a bit more interesting, I can tell it to bitwise not the value. So I'm not sure about the Python syntax, but I can write here and I can see it says it's just invert OSR. So let's try that. And yeah, let's put ff and sm.put ff and then hex sm.get. And you can see it bitwise notted this value. So cool stuff, cool way to just play with a single instruction and see what happens. To make this a bit more interesting, we are now going to connect this machine into one of the GPIOs. So for that, I'm going to add an LED, of course. Let's plug it into pin number 2. And where's GND? Also plug this to GND. And in order to use this LED in the state machine, I would need to tell it. There are like 2 ways to use the LED. One of them is the move or out instruction, and one of them is the set instruction. And we are going to use the out instruction. So for that, I'm going to need to tell the state machine that I want to have an output pin. So for that, I'm doing out init, and actually it's easier to from RP22 import PIO because there are like some constants. And then I can say PIO, I want to initialize this output pin to I think out high would be high output, or let's initialize it to low. And this still doesn't define, it only defines the machine, and it doesn't bind it to a specific pin. It just defines a piece of code and it's like dependencies. In this case, it depends on one pin, but in order to actually select the pin, I'm going to use this state machine constructor. So I can create different state machines that will run the same code on different pins simultaneously. So I can say out base, I think that would say which is the basic of the output pin. That would be pin 2 and I can have like multiple pins and then they will go sequentially from 2. So if I had like 2 items here, it would be pin 2, 3, etc. But for now, I only have 1. And then in order to write there, I can just do something like, we can remove the push, just get data, and I can move out and then the OSR. So pull gives me data, loads into OSR, and then I'm just moving this value into the out pins. And there is also the out command that can do that. Actually, not move out, move pins to move it into the output pins. My bad. And let's run that and see if that does anything. And we have the prompt, and then I can do sm.put1, and the LED is on, sm.put0, and the LED is off. And I can improve it. Like, for instance, let's say I want to, instead of like, getting the input from the user, I just want to toggle the pin whenever I get input, no matter what input I get from the user. So I can just move pin Y, and then after that, move Y, invert, I think that was the bitwise, not Y. So let's see if that works. And now every time I send data into the machine, it should just toggle the pin, no matter what I send. Yeah. So that's just a bit of playing around with input and output. I think another cool demo would be just to make it blink the pin without any intervention from me. So for that, I'm going to introduce a new feature, and that's called delay. In general, the frequency here, I mean, we could remove the pull, and then it would just toggle the pin because it would always invert these values. I think I can actually, no, I can't. Yeah, so it would just toggle the pin, but that would happen very, very fast. So you can see the pin, the LED seems like it's constantly on, because that happens 1,000 times per second. Each of those is like 1 divided by 2,000 of a second. And to fight that, I can introduce delays. And the way I write delays, I just add square brackets and number of cycles to delay. And the maximum is 31. And if I use 31, it will probably still be too fast to observe. But then I can also put a bunch of NOP instruction that do nothing. They are encoded to move YY, if I'm not mistaken. So 31, and yeah. And now it will probably blink at a rate we can actually see. Yes. And of course, we could optimize that. For instance, we could do something like, instead of running those millions of NOP instructions, we could probably have a small loop. So label loop. And then we could, I don't remember the syntax, so I'll go to the Pioasm for that. So we had like, oh, here we do have loop. So I want to instead move Y, move X, not X, or that was Y, not Y. And we had like, what did we have there? Move pins Y and Y, not Y. Move pins Y. And then we have, we don't have push. We have move X, let's say 15. And then I can just, and we can also add like delays to make everything a bit slower. And yeah, and then I can do something like jump X minus minus. So jump as long as X is not 0, and also decrement it into loop and delay 31 for each of those. Oh, not move, set X 15, my bad. Okay, and now we have this code. I can probably copy it here and hope for the best. Yeah, we can probably fix the name of this label to make it a bit more readable. And yeah, it blinks just like before, but many less instructions. We can also like set supports any value up to 31. So we can slow down the blink, and now it blinks slower. You can actually add up the numbers and calculate the cycle time. And I leave it to you as a nice exercise. I will just save it so you will be able to build on top of it. I'm going to leave it to you as a nice exercise to make this configurable. So the machine will get from the program will be able to send the machine the amount of delay instead of having this value hard coded. So obviously through pool. And then you have to do some interesting things in order to pull asynchronously. And I think we'll see that in one of the next demos. So questions. I will answer them real fast, and then we'll move on to the next demo. The first question is, X is 32 bits, that's right, but set only supports setting values up to 31. That's a limitation of set. And there are like tricks you can use in order to get larger values into X. The usual way to do it is just to pull a value from the program. So it's like the program and the PIO program work in cooperation, and the program just puts a value, and then this PIO value, this PIO program pulls in and puts it into a register. You can also like set like those lowest 5 bits with the set commands, and then shift it and set more. But in order to shift, you have to copy it to, I think, the ISR or OSR, and then copy it back. So it involves some kind of gymnastics. And PIO programs, by default, they loop to the beginning. But when they get to the end, they never stop. They always like, if you don't define anything, they will just go up to the last instruction and go back to the first one. But you can also use this like rep target and rep to create like sort of another inner loop without generating instructions. And that's useful because we have a limited number of instruction slots, and also like jump or any other commands would take clock cycles, and this allows us to save on clock cycles. Cool. And more questions, let's take them in the Q&A, because the next thing I want to show you is how we drive a 7-segment display with a PIO. And that's way more complex program, because now we have like those 8 pins that are connected to each of those segments. So each green wire controls a single segment in all the digits. Like there is segment A, this wire connected to GP2 controls these top segments in all the digits. And then we have like those blue wires connected to pin 10 through 13, and they control the each digit. So you have like to light up a combination of the right LED, the right segment and the right digit at the same time in order for this to light up. So you basically just go digit by digit and then set all the segments that you want to be on. That's called scanning. So it just happens really fast. So you do it multiple times a second. And this is the kind of thing you don't want your code to worry about. That's a perfect fit for a PIO machine. So in general, the algorithm is going to be something like that. We are going to get, let's write it in the PIO assembler. So yeah, did I paste the link to this one? What happened here? Oh, this one, yeah. I think I did. Okay, great. So basically the algorithm is going, let's call it sevseg. The algorithm is going to be something like that. We are going to get an input value from the program, what to display. And then, yeah, another great application is NeoPixels, that's true. And then there are many great applications, as we will see. This is like an example of an output, and soon we'll see an example of an input. So we get an input value from the program, and then we, for each digit, so the input value is just 32 bits, 8 bits per digit. So all 8 segments, 1 bit per segment. For each digit, output 8 bits to the pins. And then we also want to, while setting the digit pin to high, I think. I'm not sure. We just have to make sure that the pins are set like the, I don't remember if it's common anode or cathode, but we'll figure it out. I think it should be high. Yeah, I think it's like those are the cathodes, the anodes, and the segments are the cathodes of the LEDs. Never mind. Anyway, so let's do it. So first of all, we want to get an input value from the program. So we do it with pool, but that would block. So that would be annoying because it wouldn't let us update the display, and we'll fix it in a moment. But for now, let's just remember that this would block. And then the next thing I'm going to do, so pool pulls input data goes into OSR, remember, output from the program into the machine and the outside world. And then we can use the out instruction to pull a few bits out of the OSR at a time. So we can out pins 8, let's remove this. That would just take 8 bits out of the OSR and write them to the GPIO pins, and we'll define those pins in the program, just like we did with the LED. And then we are going to do it 3 times. But the thing is, each time we are pulling 8 bits, we also want to set the digit pin to high. And for that, we are going to use a nice feature of PIO that is called side set. And side set lets us set a pin to a specific value, and we can do this with up to 5 pins while executing another instruction. So this is written by just writing, I think, side, let's say, yeah, we should first of all define that we have like 4 side set pins, 1 for each digit. And I'm not sure if this is the index, the syntax, I think without this. So the first instruction, yeah, let's make them optional. Otherwise, it bails, I think. Yeah, I think it's without a parenthesis. Yeah, it has this weird thing where if you don't put this side on each instruction, it may not work correctly. There are like some restriction because yeah, it's still not happy. Yeah, let's take a quick look at the assembly reference to see how to write this. PIO assembler, values, expressions, yeah, side set, and yeah, side set value, side and side set value. So why isn't it happy? Yeah, usually like if it doesn't update the output, it means there is some error, but I don't see what, if it's optional, it's not happy. Yeah, so let's see. You know what, let's do the side on the Python, in the Python thing for now, even though I'm not very happy about this. Let's, yeah, I think it does like the binary, but you know, it's never, yeah, it does. It just doesn't like something about the syntax. Let's quickly take a look if we can spot it by checking the data sheet. Like there is probably a code example. Yeah, I think side set. Let's set side set to 1. Let's just copy this example and see if it's happy about it. Yeah. No, it's not happy. Maybe it just needs a refresh or something like that. Did it help? No, it's still not happy about something. Oh, yeah. Now I get it. Side set has to be inside a program. That's the thing. It's very picky, as you can see. Yeah, thanks Scribble for mentioning that in the chat. So yeah, so now we can probably restore our amazing creation. And yeah, and now we have this program and we can do this. We can have like a loop and then just jump loop. And then it's not happy again because we haven't set aside. But then there is this thing, if we would just, basically we just want to turn on another pin in each instruction. So this would turn on the pin for digit 1, digit 2, digit 3, and digit 4. And that would probably not work because it would work for the first iteration, but then we would shift out all the data, shift data from the OSR into, in this case, the pins, the destination. So we would shift all the 32 bits. And then when we loop, we will just have empty data. So we'll shift out zeros. And for that, we are going to use a spatial variation of pool called pool no block. And that's a non-blocking pool. And it has an interesting property. What happens if there is no data? So the data sheet says if there is no data, if there is no data, pulling from an FT FIFOs copies scratch X to the OSR. So basically, if there was no data, we'll just take the value of X. And we can do something like that, move X OSR, and that would make sure that X would always have the latest value. So whenever we pull a value from the program, we will just copy it to X, and then it will stay in X. And then the next time we loop and we execute this pull no block, it will see there is no data. So it will copy the data back from X to the OSR. And here it will copy it again from OSR to X, always making sure that X has a copy of the latest byte we received from the state machine. So I think that's probably a sketch of the solution. Let's copy this to Python and see if this works. So we can also copy the initialization code from here, just so we don't have to look for it. And in this case, we are going to have like, we have like 4 or 8 outputs. And we also have those side set pins. So we should also set side set in it to declare the side set pins. That's how we do it in Python. Let's set them to out low. If they are both low, the segments won't be on. And we have only 4 of them. If you set it to 8, it will just do crazy things and you won't be able to figure out why. And then we can also say like the out pins start at pin number, I think 2, yeah. So we have 8 pins starting from 2 to 9. And then those side set pins that control the digits start, so side set pins start from 10, I think, yeah. Side set base is pin 10. And yeah, 10 to 13, and there are like 4 of them. And if we run it, it would probably output something, or maybe not. No, it doesn't like PIO because from RP2 import PIO, we have to import it. All right, and now it's not happy. Oh, that's outload. Yeah, and another try, and it still doesn't work. Side set opt. Yeah. Oh, we are using the wrong machine. We should have used sevseg, not echo. Echo is probably a function or something, and it still doesn't work. Let's see why. Frequency outset. Let's see the value of sevseg. If it's in, no, something is very wrong here. It's like not running the code. Let's reload this page just to make sure it's updated. And hello by Pico, yes. And is it any better? Yeah, in deck, sevseg, no side set opts. Yeah, seems like we are missing something. But what could that be? I mean, we have set the output and the side set init, I think. Is that the wrong one? Let's take a look. Yeah, if you have any idea, let me know while I try to look for the answer. No side set opt in the program. I think we had it, no? Didn't we? In the Pioasm, yeah. And I think the Python doesn't need it. Like it always, as you have side set in it, it should realize there is like a side set. Yeah, I probably missed something. Let's see. Yeah. Arguments. Oh, that's a good catch. Right. Thank you, Devansh. Yeah, I always fall for that. The argument should go here and not here. And that's why it didn't find the side set configuration, because it just ignores everything you put here. So thank you, Devansh. You saved us a lot of precious time. And yeah, now you can see it writes the value that is 0 by default. So all the LEDs are on. And then we can like sm.put, and let's put FFFF0000. And this is like high turns the LED off. It's like inverted because the digits are the cathodes and not the anodes. So this would probably just have the first two one. Yeah, the highest, those two are low and those like are high. It's inverse. And in order to save time, I prepared like this array with digits, so we can use that. So instead of, it just has the segment patterns for each of the digits, and then we can just put digits 5, and it should set the lower one to 5, and then we can do digits 8 and then shift it by 8. I think that would do the trick if I did everything correctly. Yeah, 8. It's hard to tell let's do it 1. And we can basically just set the highest ones to FF to turn them off. So we have here 15. And yeah, that's like the basic thing. And I mean, we could easily create like, let's digitize a method that gets a number, and then it returns like just, you know, breaks it into digits, like let's say digits. So the lowest one is num modulo 10, and then the next one is num divided by 10 modulo 10, and the next num is divided by 100 modulo 10, and then the next one is by 1000 modulo 10 shifted by 24. And then we can have like this method digitize num and yeah, 55 just to see if it works. We should have 0055, yeah. And now we can from time import sleep, and then just have a while true counter equals 0, and then we can just sm put digitize counter. Or maybe we should call it segmentize instead of digitize, segmentize. Yeah, and then counter equals 1, and then we can sm dot sleep. Did we import sleep? I think, yeah, sleep 01. So it will count every 100 milliseconds. So let's try that, and that should probably count up from 0 very fast. So yeah, that's a cool way to test our implementation. And we have a 7-segment controller just in a few opcodes that basically, you know, runs in the PIO. So the program doesn't have to worry about refreshing the display. Let me just save it. So I will share the link with you. And there is some nice optimization that we could do, because right now we are not, some of the pins are like the digits, some of the instructions, there are like 3 instructions, all those 3, where the digits are off. It's like the display is off. So we can add delays in order to make, like we did before, in order to make sure that there is always one of the digit lit, and we can set it up in a way such as all the digits are lit for an equal amount of time. I will leave it as an exercise for you if you want to try this. I mean, it's good enough, but I wouldn't use that in production, because we can improve this by working like 5 more minutes on that. But before we move on to the next example, I want to show you that it's actually scanning the display. And for that, I'm going to show you a cool things I'm working on. It's still work in progress. But whenever you run a simulation with PIO, you will see this PIO Debugger, and it actually shows you how the program is running. And you can set breakpoints. So we can break here, and we can see the value of X, value of I, value of all the registers. And then you will see how the digits are displayed one by one as I'm moving through the instructions. So this is like the off time, and then there is 1 digit, 2, 3, 4. So yeah, so that's also a cool way to debug, and you can see the number of clock cycles down here in the cycles. Maybe it's a bit hard to see, and you can see the data shifted out of the out shift register. So this is a really cool way to just, you know, play around with PIO and get a good impression of how things work behind the scenes. And unfortunately, the actual chip, the actual silicon doesn't allow that kind of debugging, but we have a simulator, so we can let ourselves set breakpoints. You can check out like different machines. Right now, we only have one that is running, but if we had multiple. And with that, let's move to our final demo for today. And we had a demo for an output. This one is going to be demo for an input. So we have a keypad. Let's just copy, you know, all this initialization code, so we won't make the same mistakes. Just instead of seg, we'll call this keypad. We have this keypad, and we'll implement this in a moment. But what we want to do is basically just, you know, scan the keypad similar to what we did with the 7 segment, but on the input side of things. So the keypad has like 4 columns and 4 rows. And our basic algorithm is going to be, so we are going to set those like the columns start from 6 to 9 and the rows from 10 to 13, and it's a metric style. So if you like press here, it connects the first row with the first column. Or if you press here, it's the first column with the second row. So that it's like a lot of small push buttons connected in a matrix. Yeah, I love the I love the comments. Yeah, so yeah, I just enjoy reading the chat. Sorry. So basically, what we are going to do is just set those pins to set one of those pins, each of the columns one at a time to an output, drive it high, and set all of those to input with the pull down. And whenever we drive one of the pins high, if one of those input goes high, we know that the corresponding key of that row and column was pressed. So let's try to implement that. So let's write, where is this Pioasm? Yeah, let's write the basic algorithm. I think we don't even need a side set here. I mean, we could, but let's do it the other way. This time it's a program called Keypad. And what we are going to do, basically, each time set a different output pin to output. And then we can, the next thing we can do is sample the inputs to see if any of them turn high. Okay, so let's do that. So we are going to use a new command. I mean, we have used it, but not in this content, set pin dirs. And it allows us to set the pin directions of a different set of pins that calls the set pins. And there can be up to 5. So we are going to set the first one to output, similar to what we did with the side set. It's not side set, it's set, a different set of pins. And then we are going to read 4 pins so we read from pins 4 bits, shift 4 pins into the ISR input shift register. And we are basically going to do it 4 times, each time turning a different column high and shifting 4 bits. So that's the basic program. And now we can probably push this into the RX FIFO. So the software, the Python code will be able to read it. But the thing is, we can do this. We can run this as a quick demo. But the thing is, it will just spam the MicroPython. Let's just quickly set this up. So in this case, we are going to set input pins. So we will use in base starting from pin 10. So yeah, we want to, and we also want this pin to be pulled down. So I think that's the syntax. And there is also the set base, so which pins are affected by the set command, in this case, setting the pin directions. And we will start from pin number 6, those columns. So this is the set base. And now, instead of set pin it, instead of side set, let's init the set and also initialize the output to 4 pins, because we only have 4 pins that are actually, we don't have output pins. So we only have those set pins. We are not using move pins or out pins. So we only initialize them. Let's initialize them to in high. And that means that they are set to high, but to input. And as soon as we set them to output, yeah, we can, like in those set pin dirs, they will just go high. So we don't have to set the direction separately. And yeah, so this sets each of these columns pins to output one at a time, and then scanning the corresponding row from those pins. I think that's almost ready. We also need 4 I in, just to make sure all those pins from 10 to 13, all those pins are initialized with a pull up, so we can do it with pin I pin.in pin pull down, so they are 0 by default unless there is like a connection, and then they will go high. And let's print sm.get just to print what we got from this machine, and let's see what happens. Yeah, we are getting 0 because nothing is pressed. And I mean, we could, if we check the debugger, we'll see this. This is actually yeah, there is like probably some bug with wrapping around the last instruction if it's blocking. So let's just, for the sake of fixing this bug, let's use a jump here, and jump start. And now we should probably seeing, yeah, it's waiting for the RX FIFO because it tries to push, but if we type sm.rx FIFO, we can see the RX FIFO is full. This gives the how many items we have, and we can type sm.get and, you know, read the value. And I will try. No, it's too hard to like click on it and read the value at once. But we can probably do something like that. While true, print, let's print it as hex, and then time sleep 01, import time. And that's one way to go. I mean, it works. You can see when I pressed one of the pins, this turned into 40, and each print generates a different number. There is like some latency because there are like 4 items in the queue. So we have to wait until the queue cleans up. We can probably fix this latency by just, you know, pulling while sm.rx FIFO, pulling all the data from the FIFO. So when we press on something, we get 4 times the value, but immediately. But actually, there is a quick improvement we can make, and that improvement would be not to update the machine unless there is a change. And for that, we can just, you know, store the let's call this actually loop. And initially, we can store the last value in a register, and let's set y to 0. So we are going to store the last value in a register and compare the new value with the last value. And only if it has changed, then we are going to, let's do it here. So set, there is start, set y 0. And now whenever we have a new value, instead of just pushing it, we are going to move x pins. And then we are going to do this jump. If x is not equal y, is different from y, this means that we have a new value, jump new input. Let's do it with an underscore. And it doesn't generate any code because it actually needs this label. Otherwise, this is not a valid program. Then if we didn't have a new input, we can jump back to loop. And in new input, we can then push. So now we are, oh, and when we have a new input, we also want to update y with the new value of x. So this program, opposed to the previous program, is not going to spam, if we did everything correctly, is not going to spam Python with all the data that is like with data all the time. It's only going to let Python know there is something new whenever there is something new. So we can probably now change our code. Let's just paste this, and we can do while true and just print sm.get, and it wouldn't spam the console because the program would only generate values if there are new values, or maybe not. Maybe there is some bug here. Yeah, if x not move x pins. Oh yeah, right. I shouldn't move X pins. I should move the ISR because those pins are shifted into the ISR. So that's what, and that's what push is going to push. So that's a silly bug. Yeah, and let's run it and see if that works. Yeah, there is no output. Now I press 2 and you can see there is an output. It didn't stop the output. I guess I'm missing something because it generates the output as long as it's not 0. So, oh, yeah, I know what's the problem. I haven't jumped here to a loop, so it goes back to the start. And let's jump to, I mean, we can also set loop as a wrap target. So it wraps here, but by default, it goes back to the start and sets y to 0. And that's why we are getting all non-zero values, we're getting them multiple times. So let's just jump loop and let's copy this into this here. All right, and yeah, now you can see, yeah, there is like some noise, and I know why this is happening. We are shifting data into the ISR, and then in the next iteration, we are shifting data again, but we are not clearing the ISR. We need to clear it. So at the beginning of the loop, we can do move ISR null. Null is just moving all zeros into a register, a way to set it to 0. You can't use ISR with set, only with move, or with, I think without as well. Oh, no, I wanted to paste this here. All right. And I think, no, I didn't want to paste that. I wanted to paste this. Yeah. All right. And yeah, you can see now when I click on a button, it immediately spits the code. And when I stop, it says 0. I can even do 2 simultaneously. So 1 and 2, and it didn't work. Yeah, 2 and 1 works, interesting. Or 8 and 9, and then leaving 9 and pressing 9 again, leaving 8. So all sort of fancy combination. And this just runs in the background. And whenever it has something new, it lets us know. And one thing we could probably also improve, we could use this IRQ command after we push to let the software know we have new input for it. So it wouldn't have to block waiting for this input. Let's do it real quick. Let's see if we can do it real quick. So after pushing, just IRQ 0. And yeah, let's just copy this here. Just this. Actually, we don't even, we can just write IRQ 0. And then we can say sm.irq and on input, and define this function on input that gets the state machine, and then we can just copy this. We may have multiple items in the FIFO in case of fast changes, so we can do keys is sm.get, and while not sm machine, while machine.rx FIFO, while there are still items, then just read. So we always get the latest item if there are like a few, and then just print hex keys. And I think that should do the trick. And now we'll be back in the REPL, but we'll still, yeah, so we are in the REPL, but we can still get like those events while other stuff is happening. So I think that's pretty awesome. And I will save it, and you can play around with it, like creating a small functions that will actually decode those hex codes and return the names of those keys that pressed. So I think that would be a fun thing to do. But with that, we are going to wrap speaking about the PIO. And yeah, let me just share. So that's the Keypad project, and that's actually Keypad with lower p. Sorry, I'm a bit pedant, I know. And that's the, what was the other one? The 7-segment project and the Blink project. And you can play around with them. And yeah, now it's the time for the Q&A. Before we do that, a few words about how I would approach this project. I see someone already has like, already has like cool ideas for how to add a rotary encoder. The thing is, we don't have rotary encoder in the simulation yet. It's on the roadmap, but if any of you really is really going to implement that, then I'm going to prioritize that so you get the rotary encoder as well. Basically, the TV has like 2 signals that you need to drive, and then they are like combined into a single signals. I think there is like this blog post that explains how they are combined with resistors to achieve the right voltages. So you don't have to worry about that too much. I will include an explanation. I will just add this here in the final project. I will include a better explanation of how to do that in the project description. But what you basically, yeah, that's the good one. What you basically need to be doing is to generate a bunch of sync signals. There are like 2 lines, the sync line and the data line. I think you can see them here in the Pong, like there is like sync and in. And you are going to need to generate like sync signals in a very specific timing. For instance, this is a good reference image. You need to generate 5 times this long sync, which is 30 microseconds low, then 2 microseconds high, and then 5 times this short sync. Then you need to generate like 305 times these lines, which is like 4 microsecond sync, so 4 microseconds slow, and the rest is 16 microseconds high. And then you like there is like a very long state of thing, a very long list of things you need to generate, which is just a sequence of low then high pulses in different lengths. There is like this, which summarizes it pretty well, but I'm going to include the gist of this in the instruction set. And then other than the sync signal, you also need to send the data. And the data is just 0 and 1, 1 for white, 0 for black, but the timing need to be very accurate. And each pixel, I think, is like 20 nanoseconds, depending on the resolution that you want. But if you want like 128 pixels per line, then you can go with 500 nanoseconds per pixel. And you need to shift this data at a pretty fast rate. And that's why you need a PIO machine for that. And it has to be synchronized with those syncs at the beginning of each line and each frame. And for that, you will basically, I suggest to have 2 state machines on the same PIO block, so they can be reset at the same point, so they are synchronized. One state machine will only generate those sync signals, and another state machine will just read data and feed it to the data signal 1 bit at a time. So I think that's how I would go about it, and then have a buffer in the memory that would just feed information into the state machine that controls the data lines, so 32 bits at a time, scanning the memory. You can do this using an interrupt to feed the machine, or you can use the DMA if you want to experiment with another peripheral. There is like this DMA somewhere in the system description. And one of the things the DMA can do, and you are on your own here, you can do it if you like, you can skip this if DMA part if you don't, but one of the things the DMA can do, it can copy data from the memory into the RxFIFO of a state machine, so it can constantly feed a state machine. And DMA is not implemented in the simulator right now, so if you do it, let me know so I can prioritize that, so you can test it on the simulator if you want. Otherwise, you can just test it on the physical chip with a scope. That's how I did my initial testing. Yeah, if you have any questions, hop on to the Discord. So there is the link at the beginning. Any questions on the, yeah, let's just copy it here. Questions, so just stop here. And Christina will send you the description probably by the end of the week or beginning of the next week. I'm also going to post this link, so you will have a nice dice. This one is, it's less friendly, but whatever. I think this one is more friendly. So I would probably take a look at it, but I will create a short summary that summarizes the important information. And just to let you know that the simulator itself is not very picky. You can just generate one long sync signal and the horizontal sync signals without caring about all those short syncs, and it will work. So if you're not going to feed it to a real TV, you can probably take some shortcuts, but if you would really like it to be compatible with with real physical TVs, then you should do this. So again, if I'm available, so just feel free to reach out with any question. No question is too simple. Nothing is a stupid question. Every question is good. And you've seen me, like I've been coding here today, and I've made like very small specific mistake and got stuck on that for like 3 or 4 minutes. And that's, I mean, with the help of people here who helped in the chat. So it's okay to get stuck on something. It's not stupid. Oh, yes, you have a cat. That's so cute. So it's totally okay to get stuck and ask a question, and other people you can usually spot this thing in like a few minutes if you are stuck on something. So feel free if you need anything. And yeah, as I said at the beginning, I love seeing what people are doing between the classes or now after the classes, like what PK and Scribble have been doing in the Discord. I don't think they are here anymore, and Pioasm, I see, I also saw a lot of chat comments, so please keep them coming. All right, Christina, I think we can call it a course this time.